Hello. I want to spend a couple of minutes going over lab number 4, friction, to give you a few insights and to hopefully ease your ability to do that one. On the face of it, it's a pretty simple question, but it's a little more complex than that. So hey, I guess the first piece we can take a peek at is just the idea here that we can slide one book across the other and it heats up. That the energy is the energy of sliding one book across the other, because friction is present, and we can increase that by squeezing down harder or not as much. Because friction is present, that energy we put in sliding it back and forth is converted into other forms. Heat, sound, probably not the sound we're hearing, but heat and sound are two common forms of energy, that like mechanical energy sliding one thing across the other. Just rub your hands together and you can feel heat. Because that's transformation of kinetic energy into another form of energy by way of friction. So this question that we were given can be answered in multiple different ways. One of the wonderful things about physics is that if it's true in all sorts of different ways. You're not harnessed to one simple approach to answer the question. And one of the frustrating things about physics is a lot of people just, how am I supposed to solve the problem? Just tell me what I have to do. And when I say, oh, well, you could take a couple of different approaches, it's annoying. So one way to answer this question is with Newton's laws and a simple kinematic question. So the question that we have a 5 kilogram chemistry textbook that we're going to push across the floor. We're going to give it a kick, a shove, just send it sliding across the floor. And once we get it moving, it's moving at 15 meters per second. But friction is present. The coefficient of kinetic friction is 0.52. How far will the book slide after we give it the push, after we give it the shove? How far will it keep sliding before friction stops it? So we want to make sure that we do free body diagrams. We want to make a image of what's going on here. So we draw a book on a horizontal surface. We're giving it a shove. It's moving 15 meters per second. Motion is opposed by friction. So there's a force due to friction. And that force is going to be kinetic friction, coefficient of kinetic friction times the normal force. So this book has weight, which is mg. So it was 5 kilograms. 5 kilograms times 9.8 meters per second squared. We can figure out that there is a downward force, 5 times 9.8, 49 newtons, the weight of the book. Oh, I lost myself. 49 newtons. Therefore, the normal force, equal and opposite to the weight, is also 49 newtons. And so the frictional force would be the coefficient of friction, 0.52. 0.52, that's a 0.52, times 49 Newton normal force. That means the frictional force, 0.52 times 49, is 25.5 newtons. Okay, so what do I know? What am I looking for? I want to know how far it will slide. The net force in the x-axis is going to be the force that is pushing it to the right minus the force that is pushing it to the left, that is resisting motion. The force that is pushing it to the right is nothing. There is no force pushing it to the right. By the time we come on the scene, this thing is sliding with a velocity of 15 meters per second. I don't know what force made it slide at 15 meters per second, but it's not acting on it anymore. Right now it is sliding at 15 meters per second and subject only to friction to slow down. The reason it is moving is because it is moving. That sounds weird. The reason it's moving is because of inertia. It's an object in motion that tends to stay in motion at constant velocity in a straight line unless a net force acts on it. So right now, there is 0 newtons of force pushing it to the right, but there are 25.5 newtons resisting that motion, tending to slow it down. So the net force in the x-axis is negative 25.5 newtons. Since force equals ma, Newton's second law, ma equals negative 25.5 newtons. Therefore, the acceleration, negative 25.5 newtons, divided by the original mass, that was 5 kilograms, 5 kilograms. 25.5 divided by 5, negative 5.1, negative 5.1 meters per second squared. That is the acceleration of the book. All right, hold on to that thought. Negative 5.1 meters per second squared, because I need to give myself more space to write. All right, so now we have a kinematics problem. So known and unknown. What do we know? We know when we came on the scene, the book had an initial velocity of 15 meters per second. We also know the acceleration of this book, negative 5.1 meters per second squared. We just determined that based on the net force and the mass of the book. We also know that the final velocity of this book, before friction stops it, is 0 meters per second. I don't know how far it travels, and I don't know how long it takes, how much time elapses during this event. But I don't care about how much time it takes. So I have my 5 kinematic variables accounted for, and I've determined which one I don't want to be in my final equation. When I look at my equation sheet for the equations of kinematics, I find that the one that doesn't have time in it is v squared equals v naught squared plus 2ax. I want to solve for x. First step algebraically, subtract v naught squared from both sides of the equation. Second step, I divide both sides of the equation by 2a, 2 times the acceleration. And I get, after I do that, the 2's cancel, the a's cancel, x is all by itself. I get x equals v squared minus v naught squared divided by 2a. V, the final velocity was 0, 0 squared minus positive 15 meters per second squared divided by 2 times negative 5.1 meters per second squared. Got to be careful with the math here. I recommend doing this even though it seems like a pain. 15 squared is 225. So 0 minus 225 is negative 225 meters squared per second squared in the numerator, divided by 2 times 5.1. 2 times 5.1, it's negative 10.2 meters per second squared in the denominator. When you do the math here, cancel out the units, squared cancels out, meters cancels out with one of them. We wind up with units of meters. So it's negative 225 divided by negative 10.2. Oh, 225 divided by, oh, come on, 225. My calculator has decided to be bad. 225 divided by 10.2, and we get 22.05, so I'll call it 22 meters. Negative 225 divided by negative 10.2 is positive 22 meters. That is the kinematics approach. There is another approach that is accessible to us shortly, which is conservation of energy. Which is to say that friction does work of friction equals the change in kinetic energy of the book. The work of friction will be work equals force times distance. So the force of friction was the 49 times 0.52, the 25.5 newtons. 25.5 newtons times distance, x, equals the change in kinetic energy. Kinetic energy is 1/2 mv squared. The book went from traveling at 15 meters per second to 0. So 1/2 times 5 kilograms times 15 meters per second squared. The amount of kinetic energy that the book had at the start of this event, 15 squared times 5 divided by 2, had 562.5 joules of kinetic energy, which equals the work that friction did. So friction was 25.5 newtons times the distance it traveled equals 562.5 joules. So the distance x equals 562.5 joules divided by 25.5 newtons by 25.5. And that too gives us an answer of 22 meters. Two different approaches based on different concepts. Some of the concepts fit into our exam 1 material where we had kinematics and forces, including frictional force. Some of the concepts fit in after exam 1 when we talk about work and energy and conservation of energy. So this lab kind of bridged the two. You could have either approach, and that's how we would solve this one. Either way works, it's the right answer. Okay, I will return in a bit.